Imagine a single glass of water. Just one ordinary glass. Now, what if I told you that the energy locked inside that water could power your entire home for a whole year? No coal, no oil, no solar panels covering your roof. Just water. Sounds like science fiction, right? Like something out of Star Trek or Iron Man. But here's the thing, it's not fiction anymore. We're talking about fusion energy. The same process that powers the sun. The same reaction that makes stars burn for billions of years. And right now, at this very moment, scientists around the world are on the verge of cracking the code. We're talking about a technology that could generate unlimited, clean energy with virtually no pollution, no nuclear waste, and no risk of meltdowns. And when we finally figure this out, we're looking at what could easily become the next trillion-dollar industry. This isn't just about making electricity cheaper. This is about changing everything. Climate change solved. Energy wars over poverty in developing nations massively reduced. We're talking about a complete transformation of human civilization. So today, we're diving deep into the world of fusion energy. What it is, why it's been so impossibly hard to achieve, and why, after decades of failure, scientists are finally saying, we're almost there. Let's get into it. Alright, so let's start with the big question. What makes fusion energy so special? Why have we spent over 70 years and tens of billions of dollars chasing this technology? To understand that, we need to talk about what fusion actually is. See, there are two ways to get energy from atoms. The first way is fission. That's what we've been doing since the 1940s. You take a big, heavy atom like uranium, and you split it apart. When you do that, it releases a ton of energy. That's how nuclear power plants work today. But fusion is the opposite. Instead of splitting atoms apart, you smash them together. You take two tiny atoms, usually hydrogen and D, force them to collide with so much energy that they fuse into a single heavier atom. And when that happens, boom, massive amounts of energy are released. Now here's the crazy part. Fusion produces about 4 times more energy than fission. 4 times. And unlike fission, fusion doesn't create long-lived radioactive waste. You're not dealing with spent fuel rods that stay dangerous for thousands of years. The main byproduct of fusion is helium. You know, the stuff in birthday balloons. Completely harmless. And the fuel. This is where it gets absolutely mind-blowing. The primary fuel for fusion is deuterium and tritium, both forms of hydrogen. Deuterium can be extracted from seawater. We're talking about an energy source that's literally as abundant as the ocean. 1 liter of seawater contains enough deuterium to produce the energy equivalent of 300 liters of gasoline. Let that sink in for a second. If we mastered fusion energy, we would essentially have unlimited power for millions of years. No more dependence on oil. No more coal mines destroying landscapes. No more geopolitical tensions over energy resources. Just clean, abundant, safe energy for everyone. So, yeah, that's why it's called the Holy Grail of energy. Okay, so if fusion is so amazing, why don't we have it already? Why are we still burning fossil fuels like cavemen when we could be harnessing the power of the stars? Well, because fusion is really, really hard. To understand why, let's talk about what actually has to happen for fusion to work. Remember, you're trying to force 2 atoms to smash together. But here's the problem. Atoms don't want to touch each other. They're surrounded by electrons, and electrons have a negative charge. When 2 negatively charged things get close, they repel each other. It's like trying to push 2 magnets together. The closer they get, the harder they push back. So, how do you overcome this? You need to give those atoms an absolutely insane amount of energy. We're talking about temperatures over 100 million degrees Celsius. That's about 6 times hotter than the core of the sun. Yeah, 6 times hotter. At those temperatures, matter doesn't exist as a solid, liquid, or gas anymore. It becomes something called plasma, superheated soup of charged particles. And here is where things get even more complicated. You need to keep that plasma contained and stable long enough for fusion to happen. But how do you contain something that's hotter than the sun? You can't use a metal container. It would vaporize instantly. You can't use ceramic, glass, or any material known to man. Nothing can withstand that kind of heat. This is the central challenge of fusion energy. It's not that we don't understand the physics, we do. The problem is engineering. How do you build a machine that can create and sustain these conditions? How do you bottle a star? For decades, the answer was, we can't. Scientists tried. Oh boy, did they try. But every time they got close, something would go wrong. The plasma would become unstable. The magnetic fields would fail. The energy required to start the reaction was always more than the energy they got out. In fact, there has been a running joke in the fusion community for the past 50 years. Fusion is 30 years away, and always will be. But something's changed, and that's where things get really interesting. December 5th, 2022. That's the date that changed everything. At the National Ignition Facility in California, a massive research lab funded by the U.S. government scientists achieved something that had never been done before. They created a fusion reaction that produced more energy than it consumed. Let me repeat that. More energy out than in. This is called ignition, and it's the holy grail of fusion research. For the first time in human history, we proved that fusion energy isn't just theoretically possible, it's practically possible. Here's how they did it. The National Ignition Facility uses an approach called inertial confinement fusion. Imagine a tiny pellet about the size of a peppercorn filled with deuterium and tritium. This pellet is placed inside a chamber. Then, 192 of the world's most powerful lasers all firing at the exact same moment blast that pellet from every direction. The lasers don't actually hit the fuel directly. Instead, they heat up the outer shell of the pellet so fast that it explodes inward. This implosion compresses the fuel to incredible densities and temperatures enough to trigger fusion. For a brief moment, a fraction of a second, you've created conditions similar to the core of a star. And on that day, in December 2022, they got it right. The lasers delivered about 2.05 megajoules of energy to the target. The fusion reaction produced 3.15 megajoules. That's a 50% energy gain. It might not sound like much, but in the world of fusion, this was like landing on the moon. The breakthrough made headlines around the world. Scientists who? Okay, so we achieved ignition. We got more energy out than we put in. Problem solved, right? Time to start building fusion power plants and say goodbye to fossil fuels? Not quite. See, there's a big difference between a scientific breakthrough and a practical energy solution. Yes, the fusion reaction produced more energy than the lasers delivered. But those lasers themselves, they've required about 300 megajoules of electricity from the power grid just to operate. So when you look at the total energy balance, the energy needed to run the entire facility, we're still way in the negative. It's like saying you made a profit selling lemonade, but ignoring the fact that you spent $10,000 on the lemonade stand. Beyond the energy balance, there's also the question of speed. The National Ignition Facility can perform this experiment maybe once a day. A commercial fusion power plant would need to trigger these reactions multiple times per second. Constantly. Reliably. For years on end. And then there's costs. The National Ignition Facility cost over $3.5 billion to build. Those lasers, not cheap. The facility needs an army of scientists and engineers to run. This isn't something you can just scale up and plop down in every city. So yeah, we've proven fusion is possible, but turning it into a practical, affordable energy source, that's still a monumental challenge. But here's the good news. We're not starting from scratch anymore. That breakthrough was a proof of concept. It showed the world that fusion isn't some pipe dream. It's real. And that's attracted a wave of investment like we've never seen before. For most of fusion's history, research was dominated by governments, big national labs. Massive international collaborations like ITER in France, a project involving 35 countries. These projects move slowly. They're cautious, built on decades of bureaucracy. But something shifted in the last 10 years. Private companies started getting into the game, and they brought a completely different approach. Move fast, take risks, and innovate. Today, there are over 30 private fusion companies around the world, and they've raised billions in funding. We're talking about serious money from serious investors like Jeff Bezos, Bill Gates, and Peter Thiel. These aren't people who throw money at sci-fi fantasies. They invest in technologies they believe will dominate the future. Let's look at a few of these companies. First, there's Commonwealth Fusion Systems, or CFS. They're a spin-off from MIT, and they've raised over $2 billion. Their approach uses a tokamak donut-shaped reactor that uses powerful magnetic fields. What makes CFS special is their new high-temperature superconducting magnets. These magnets are way more powerful than anything we've had before, which means they can make smaller, cheaper reactors. Then there's TI Technologies. They've been around since the late 90s, but have recently made huge strides. They use a completely different approach called a field-reversed configuration. Instead of the usual fuel, they're working toward hydrogen-boron fusion, a reaction that produces almost no neutrons. This means even less radiation and easier reactor designs. And there's Helion Energy, backed by Sam Altman of OpenAI. Helion's aiming to have a commercial fusion plant producing electricity by 2028. That's just a few years away. Now, a lot of experts are skeptical about that timeline, but the fact that a company is even making that claim shows how much the field has progressed. These companies aren't just building reactors, they're building an entire industry, supply chains, talent pipelines, partnerships with utilities. They're treating fusion like a startup, not a science project. And that speed and agility could be exactly what we need to finally crack this puzzle. The fusion gold rush is on, and it might just change the world. So when can we actually expect to flip a light switch powered by fusion energy? The honest answer is, it really depends on who you ask. The big international project, ITER, isn't expected to achieve its first plasma until 2020, and they won't even attempt full fusion until the late 20s or 30s. After that, they'll need to build a demonstration power plant, which won't be online until the 2040s or even the 2050s. So, if we rely solely on that traditional government-led approach, we're looking at maybe 30 years before fusion powers our homes. But the private companies, they're moving way faster. Commonwealth Fusion Systems says they'll have their pilot plant operational by 2025 or 2026. If that works, their commercial plant could be producing electricity by the early 2030s. Helion is aiming for 2028. TA Technologies is targeting the early 30s. Now, are these timelines realistic? Maybe, maybe not. Fusion does have a long history of over-promising and under... But here's the thing. The progress we've seen in just the last 5 years is absolutely staggering. Technologies that seemed impossible a decade ago are now being built in labs and warehouses. The National Ignition Facility's breakthrough proved the physics works. Now it's a race to perfect the engineering. My personal prediction? We'll see the first commercial fusion power plant producing electricity sometime in the early to mid-2030s. And once that happens, the technology will scale rapidly. By 2040 or 2050, fusion could be a major part of the global energy mix. All right, let's dream a little. Let's imagine fusion actually works. What does that world look like? First, energy becomes cheap, like really cheap. Right now, electricity costs vary wildly, but with fusion, fuel costs are almost nothing. You're pulling deuterium from seawater. The operating costs would be minimal. Electricity prices could drop to a fraction of what they are today. And when energy is cheap, everything changes. Desalination becomes affordable, turning seawater into drinking water for billions. Vertical farming becomes viable, letting us grow food anywhere. Electric vehicles become the obvious choice, because charging them costs next to nothing. And climate change, fusion could be the silver bullet. Fossil fuels become obsolete. No more coal plants, no more oil drilling, no more fracking. Carbon emissions would plummet. We might actually hit those net zero targets that seem so impossible right now. Geopolitics would shift dramatically. Think about how much global conflict is tied to energy resources. Wars over oil control over gas supplies. When energy is abundant and cheap for everyone, those power dynamics vanish. And here's something people don't talk about enough: space exploration. Compact fusion reactors could power spacecraft. Right now, getting to Mars takes 6 to 9 months. With fusion-powered propulsion, we could cut that time in half, maybe even less. This isn't just an energy revolution. It's a civilization revolution. So, is fusion energy the next trillion-dollar tech breakthrough? Honestly, yeah, I think it is. Look, we've been chasing this dream for 70 years. For most of that time, it felt like a mirage. But something's different now. The breakthroughs are real. The investment is real. The momentum is real. We've proven that fusion works. Now we just need to make it practical. And yes, that's a huge challenge. But it's an engineering challenge, not a physics problem. And humans are really, really good at engineering. Think about it. 120 years ago, the Wright brothers flew for 12 seconds. Fast forward, and we have supersonic jets and reusable rockets. 50 years ago, computers filled entire rooms. Today, you have more computing power in your pocket than NASA had to put a man on the moon. The point is, when humanity focuses on a problem, we solve it. It might take decades, but we figure it out. Fusion energy is that next frontier, and once we crack it, there's no going back. We'll look back at fossil fuels the same way we look at steam engines, relics of a primitive past. So yeah, keep your eyes on fusion, because in 10, 20, maybe 30 years, it might just change everything. And hey, if you made it this far, thank you. Seriously. If you enjoyed this deep dive, hit that subscribe button. We're covering the biggest tech breakthroughs every week. Drop a comment below. Do you think fusion will happen in our lifetime, or are we still decades away? Until next time, stay curious, stay hopeful, and keep looking forward. Because the future, it's going to be bright.